Hey, Algebra 2, this video is going to talk about exponential growth and decay problems. So remember that an exponential function looks like this. You've got y equals, the key is that there's this base raised to an unknown power right here, and then it might have a number in front of it, it might not, and then it might have a number out here at the end, it might not. So the base here, this is the number that matters. If it has a number in front, that's just going to maybe make it taller or shorter by a little bit. This base is what matters. So if this base is greater than 1, and it doesn't have to be a whole number, if 1.3 is still greater than 1, then it's exponential growth. So that means, in general, the graph of the function from left to right goes up over its trajectory. If this number is between 0 and 1, if you want to just say it's less than 1, but it won't be negative. So if it's like 0.5, 2/3, 1/4, anything like that, 0.75, anything less than 1 but greater than 0, that's decay. And think about decay is like decrease. The graph would have a downward trajectory from left to right. It comes down very quickly. The other big thing about these functions, they have this asymptote on the bottom. That's what we call it when a graph flattens out. So these functions always have an asymptote on the bottom. And if you're looking at this formula, this last number out here, this k, that tells you the asymptote. So if I had a function like y equals 2 times 1/2 to the x minus 3, I know this is a decay function. How do I know that? I know that because the base, the number being raised to the exponent, is smaller than 1. 1/2 is smaller than 1. So this 2 out front here, in terms of deciding growth or decay, it doesn't matter at all. And then this number out here, remember, that's our horizontal asymptote. So the equation of the horizontal asymptote would be y equals -3. And if we were looking at the graph of this function, really, we would know that it's going to flatten out on the bottom here at -3, and then it's going to be decay function. Okay, now you could always plug points in, but even if we just needed a sketch, it's going to do something like this, right? I know this bottom flat part is going to come to -3, and then I know it's going to have this general downward shape because it's decay. So that's just a quick refresher on the graphing part. Now, where those go even a little further is when we talk about compounding interest or problems with exponential growth or decay. So if I have like this formula, this is just for general growth or decay. So you'll see this in problems like, the population of water buffalo in a certain state. It began at 65, and then let's say that the water buffalo population is growing at a rate of 1.3% every year. So it began at 65 water buffaloes. It's growing at a rate of 1.3% per year. And how many water buffalo will there be in 5 years? Okay, so if it started at 65 in whatever year we're counting, 5 years from then, if it's growing at a rate of 1.3%, how many will there be? So in this formula, this P right here, this is the principal or the initial value. So that's where our 65 would go, our starting value of water buffalo. Okay, and then notice this says plus or minus, 1 plus or minus r. We choose a plus or a minus depending on whether it's growth or decay. So since this one is growing, we're going to use plus. So it's 1 plus, and then r is the rate. So the rate at which the population is growing is 1.3%, but we have to convert that to a decimal. So remember, converting a percent to a decimal means dividing by 100, which really just moves the decimal place backwards 2 spots, because when you divide by 100, you just bring the decimal back. So 1.3% is 0.013. One other thing that just kind of helps me is when we're talking about percentages. So these are not zeros, these are like decimal places. Okay, here's the decimal. So there's one place. This hundredths place right here would be 1%, 2%, 3%, 4%, 5%. This is the units for percent. So if it were 50%, it would have to go over here and be 5 zeros. If that helps you remember, awesome. If not, just divide by 100. So we put our rate as a decimal into the R spot. And then the last thing we need is the T. T is the time. So they asked us how many would there be in 5 years. So that means that our time is 5. So we're just going to put in 5. So then you're going to type this expression into the calculator just like it looks with the parentheses and everything. You want to type all that in. Okay. So I'm going to type this in, exponent of 5. All right. So I put this in my calculator and I got 69.336. 69.336. So that would just be 69 because we can't have 0.3 of a buffalo. All right. There would only be 69 buffaloes. So that's like about basically one is being born each year. And that's because that growth rate is really low. If you had a growth rate of like 10 or 20%, this would be a lot higher. Also, if we had more years, this would be a lot higher. So that's growth. You would know to use the 1 minus if it said something like depreciate. A car or a phone or something depreciates in value. Depreciate, decrease, anything like that. Okay.